What is going on, guys? Welcome back. In this video today we're going to train and evaluate multiple machine learning models for heart disease detection. So let us get right into it. Alright, so we're going to do heart disease detection in Python today, and for this we're going to train multiple machine learning models on the same data set. We're going to compare them in terms of their performance, and then we're going to try to maximize this performance by doing hyperparameter tuning, and in the end we're also going to take a look at the feature importances. So we're going to analyze which of these features down below are particularly important when it comes to detecting whether someone has a heart disease or not. Now, this dataset is a little bit special because usually when I do these machine learning projects or machine learning processes, I use datasets where we have to do a lot of pre-processing. So we have some features that are textual or categorical that need to be turned into numerical features. This particular dataset here already has only numerical features. So we can see that we only have numerical values here, even if we display all the features. We can see that all of them are basically numbers, so either binary or numeric, even the categorical ones. And because of that, we don't really need to do any pre-processing here. We can just go ahead and use the data right away. Of course, you can do feature engineering in terms of creating new features if you want to. You can maybe also think about taking something like chest pain type here and splitting it into multiple columns. So basically doing one hot encoding. You can do that if you want to. But today we're going to focus mainly on training, comparing, evaluating, and also analyzing the feature importances. So you can see we have a bunch of features here that are quite interesting: chest pain type, blood pressure, maximum heart rate, and so on. And then we also have this target, which is a binary feature, basically, or a binary target, 0 for no disease and 1 for disease. And this is what we're trying to predict here. So that is our classification task, so to say. Now, the column names can be a little bit difficult to understand. CP stands for chest pain. Col stands for cholesterol. Then we have T, rest, BPS stands for resting blood pressure. So if you don't know what a feature means, just go to this Kaggle page and look it up in this box up here. Other than that, you don't really need to know what you're working with while you're working with it, except for knowing what kind of data it is: categorical, binary, numeric, and so on. So you will find a link to this dataset in the description down below. Just download it, extract it, and then you can open up a Jupyter notebook and load this CSV file using pandas. Speaking of that, we're going to also install a couple of packages. So open up your terminal and use pip to install pandas, matplotlib, seaborn. I think we're also going to use numpy, and of course we're going to use scikit-learn. These are the packages that we're going to need in this video today. Make sure you have them installed. And once you have this, we can start by importing pandas as PD. And then we're going to say the data set is going to be PD read CSV heart CSV. And we can take a look at this. You can see, again, all of these features are numerical features. We can use them right away. For some models, we will have to do some scaling because some models are scale sensitive, others are not. But what we're going to do now is we're going to just take this data right away, turn it into X and Y, and then do a train test split. So we're going to say from scikit-learn.model selection import train test split. Then we're going to say the X and Y data is going to be the data when we drop the target is going to be the X data, so the input data, and Y is going to be just the target. And then, of course, the train test split is going to be X train, X test, Y train, Y test. That is going to be splitting X and Y. And we're going to choose a test size which is quite high today because this data set, let's say the models do quite well if you just use 20% for the testing set. So if you use 80% for training, the accuracy and everything is going to be quite high. So we're going to make it a little bit more difficult by providing less data. So I'm going to go with a test size of 40%. So if this was a different data set, you would want to go with something like 20% for test size. But in this case, we're going to train on 60% of the data and evaluate on 40% of the data. And we're also going to provide a random state, 9 for neural 9, just to make sure we have the same results every time we run this, because otherwise, of course, it's random. So xtrain, xtest, ytrain, ytest. And then we're going to start with the scale insensitive models. So some of the models don't really care about scale. So insensitive. One such model would be a random forest classifier. Another one would be naive Bayes. Another one would be gradient boosting. So we're going to just go ahead and say from scikit-learn dot ensemble, we're going to start with a random forest classifier. I'm going to say forest is equal to random forest classifier, and we're going to train this random forest classifier on X train and on Y train. So now we're going to repeat this process for the different model types. I'm going to just copy and paste this. I'm going to replace this by a Gaussian naive Bayes classifier. So I'm going to say NB CLF is going to be naive Bayes or Gaussian naive Bayes. NB CLF fit, same as before. And then we're going to also say, I think it's still ensemble, import, what was it, gradient boosting classifier, GB CLF. I think this one should be scale independent. Usually you only have scale dependent models when they're caring about distances that are like Euclidean geometric distances. I'm not sure if that's entirely true what I'm saying right now, but I think that gradient boosting should be scale insensitive, unless there's some distance measure in there, but I think it shouldn't be. So we're going to say gradient boosting classifier. We're going to say GBCLF. We're going to train. And now we have 3 models trained on the data. We're going to evaluate them in a second, but let's also add 3 more that are scale sensitive. So I'm going to say scale sensitive models, and we're going to train a simple k-nearest neighbors classifier. But for this, of course, we need to first scale the data. So we're going to say from scikit-learn dot preprocessing, we're going to import the standard scaler. We're going to create an instance of it, and we're going to scale our training data. So we're going to say xtrain is going to be equal to scalar fit transform. So we're going to fit the scalar on the data, and we're going to also transform the data. And of course, this should result not in xtrain, but in xtrain scaled. And the same thing will be done for the test data, but we're not going to fit again for the test data. We're going to just transform. There you go. And now we're going to say from scikit-learn dot neighbors, not naive Bayes, neighbors, import k-neighbors classifier. K&n is going to be equal to k-neighbors classifier. We're going to always use the default hyperparameters, and we're then going to tune the model that performs best. So k&n is going to be k-neighbors classifier. K&n is going to be fitted onto xtrain scaled and ytrain. Why don't we have to train? Why don't we have to scale the y data? Because of course k&n and all the other models are only focusing on the input, and the output doesn't really matter. The output is just the output. It's just the value that the model produces. In the case of k-nearest neighbors classification, it's just the color of the dot, the number that's associated with the class. In our case, it's binary, so it's 0 or 1. We don't really need to scale that. It doesn't make a difference. We only need to scale the training data, so the input data. Yeah, not the training data, the input data. We also need to scale the test data, the input of the test data. So we fit the model here, then we copy this, we paste it, and we're going to also train a logistic regression. So linear model, or yeah, logistic regression. Even though it's called regression, it's actually a classification. So we're going to call this log logistic regression, log fit. And then finally, we're going to train a support vector machine, a support vector classifier, and there you go. So we have these 6 models now, and we're going to evaluate them, first of all, in terms of accuracy. That's quite simple. All we have to do is we have to say dot score and then x test and y test. So like this, the forest performs quite well. And we're going to do the same thing now for the other models. We're going to do for the naive Bayes classifier the same thing, for the gradient boost the same thing. And then we're going to do a slightly different thing for the k and n, because here we're going to say x test scaled y test. We're going to then copy and paste this. So we're going to say log, we're going to say SVC, and we can see actually that the forest performs the best and the gradient boost, then the support vector classifier. So in terms of accuracy, this one is the best. Now, you could say right now we're working with medical data, and I'm not a medical professional. I don't know if that's correct and how they make the decisions, but my opinion is, or my feeling is that it's not so bad if I say someone might have a heart disease and then they are healthy. That's not that much of a big deal. It's way more problematic if I say, hey, someone's healthy and then they have a heart problem or heart disease. So recall is more important, in my opinion, than precision. Now, for those of you who don't know what recall is and don't know what precision is, accuracy just tells us how often am I right about my prediction. Precision tells me when I say someone has a heart disease, how often am I right about this? This is not the same. So accuracy says I make guesses. Let's say I make 100 guesses. So this is accuracy. I make 100 guesses, and out of these 100 guesses, I have, let's say, 80 correct. That would be an accuracy of 80%, or in our numbers up here, 0.8. Now, precision is different. Precision is not how many guesses do I have. Precision would be, I don't make 100 guesses, but let's say I make 200 guesses, doesn't really matter. But I say 100 times that the patient has a disease. How often when I say that they have a disease, not how often when I say something in general, how often when I say they have a disease, am I correct about this? If I have a precision of, let's say, 20%, so 20 times I'm actually correct about this, my precision is 20%. Recall asks a different question. Let's say that there are actually 100 patients with heart disease. Recall asks, how many of them do I find? So if I say that every single one of the patients has a heart disease, my precision, so if I say 200 have disease, but actually only 100 actually have one, my precision is 50%. But my recall is 100% because I can find all the patients with heart disease. So if I always say yes, of course that's not intelligent, but the recall is the important thing because I want to spot every patient with a heart disease. This is at least my reasoning. I don't know if that's what doctors think, but this would be my reasoning, that recall is way more important. I want to find all the patients with heart disease. It's okay if I say someone has a heart disease and then they don't have a heart disease because, still a human expert could take a look at it, but it's better if I give you a false positive than a false negative. This is my reasoning. So we're going to see how well the models perform in terms of that. We're going to say from scikit-learn .metrics import the recall score. And we're going to say that the predictions of the forest model are going to be making predictions on the test data, and then we're going to say that forest recall score is going to be recall score of the actual results and the predictions. So in this case, we would have a recall of, actually, no, it's not the same, but it's quite similar to the accuracy. We're going to take this now, we're going to copy it 3 times, or actually I should only copy 2 times. But we're going to change this now to be equal to, what was the other one? Naive Bayes, classifier, NB, Then I'm going to change this to gradient boosting classifier GB. And we can see that the recall for the gradient boosting is actually the same as the one for the forest. So if we care about this, they are actually the same. But of course, the forest has more accuracy, so probably it has higher precision as well. And now we can go ahead and copy this and do the same thing for K and N, but this time with the scaled data. The rest stays the same. And now we can copy this twice. We can change this to log. We can change this to log. And finally, we have SVC. And we can change this to SVC. So for the recall, either the forest or the gradient boosting classifier seems to be the best choice. And because of that, we're going to focus on the forest from now on. We want to know how good we can get by using the forest. Now, it's not a guarantee, by the way, that hyperparameter tuning will necessarily improve the model. Now, I'm not sure actually, or actually I could be sure if I look at the results. I'm not going to do it right now. But I'm not sure if our forest is going to necessarily become better by hyperparameter tuning. Actually, I wanted to use for the forest as well a random state. So I'm going to say random state is equal to 9 and run all of this again. I think it stays the same. But the idea is that hyperparameter tuning can have a good effect if I maybe have more data, if my model maybe, or if the data is more complicated, I don't know. But it's not a guarantee that hyperparameter tuning will produce the best model because, of course, we're doing cross-validation, or maybe we're using a validation set, but we're not actually working with the test data. So we're evaluating the model on the test data, but we're doing either cross-validation or we're using a validation set to do the hyperparameter tuning, which means that we're optimizing for different data. So we don't have a guarantee for this. But before we do that, I want to also plot another metric, which is the ROC, which I forgot what it stands for. But we have the ROC and the area under the curve. This is a plot that plots the false positive rate on the x-axis and the true positive rate on the y-axis. So basically the recall on the y-axis and then also the false positive rate on, so how often I misclassify something as positive even though it's negative. And this curve shows us the trade-off between these two metrics. So we're going to say import matplotlib as, or matplotlib pyplot as plt. From scikit-learn, we want to also, from scikit-learn metrics, we want to import the ROC curve and the ROC AUC score, area under the curve. And what we're going to do here now is we're going to say, give me the probabilities. So the forest can give us the probabilities, not just the classifications. I think that a k-nearest neighbors classifier cannot do that. I think KNN does not have a predict prop a function. Oh, actually it does. So which one does not have it? Does the SVC have it? It actually has it. Didn't think so. So maybe all the models that we trained have that. So the logistic one definitely has it. Yeah, maybe they all have it. But we're going to get the probabilities from the forest by calling the predict prop a function, and we're going to say predict based on the test data, make predictions, and then we're going to plot this curve. So we're going to get the false positive rate and the true positive rate and the thresholds by calling the ROC curve function onto y-test and the y probabilities. So basically the idea is we get some probabilities and we say, okay, after a certain probability, I'm going to classify this as a disease, as a yes, and below that I'm going to say no. And the question now is what threshold leads to what kind of FPR and TPR, actually not TRP, TPR, true positive rate and false positive rate, and we're going to plot this trade-off. So we're going to say PLT plot FPR TPR PLT X label. We're going to say on the x-axis we have the false positive rate On the y-axis, we have the true positive rate, also called recall. And the title is going to be just ROC curve. I'm going to say PLT show. And this is going to give us nothing because there's a problem. What is the problem? Y test, Y probabilities. Oh yeah, we need to say we want to have this. Just a second dimension here. So that is the curve. In this case, it doesn't look too interesting because the model performs quite well. We can also see that by calculating the area under the curve, which is like a discrete interval of everything below this area. One is perfect, and I think we're going to get something pretty close. So y test, y props. This gives us almost 0.99. But yeah, this is basically the trade-off. Maybe if we want to talk about this, we can use a different model. Maybe we can go with log and see that this looks different now. And this has a way worse area under the curve. But the basic idea is I want to maximize the recall, but I also don't want to, destroy my precision. So this is basically the opposite of precision. How often am I wrong about my positive guesses? And how many of the positive instances do I find? This is a trade-off. And in order to get, for example, to 100% to find all of them using this not so good model, I would have to basically classify everything as a disease, because only then can I get 100%. But I can get a pretty good performance already by just missing 65% or something like this of the negative instances. So this is not a good model. You can see the trade-off is not very good, but I can maybe change this and do this. Yeah, SVC doesn't have predict probability. Okay, so this was the model that doesn't have it. KNN, does KNN have it? Yes. So for KNN, I can get not so good recall, around 80%, but I also miss quite a lot. So this is also not a good model to do that. If I go with the gradient boost classifier, in order to get 100% recall, so to find all the diseases, I would have to allow for something like 22% of false positive rate, which means 22% of the time when I say something is actually a disease, it's actually not a disease. Yeah, so this is also a pretty good model, but the best one seems to be the forest. So we're going to keep working with the forest, and for that we're going to do hyperparameter tuning using grid search. So we're going to open up a new section here. We're going to say hyperparameter tuning, and we're going to say from scikit-learn.model selection import grid search CB. The parameter grid is going to be equal to a bunch of different hyperparameters. These come, of course, from the model. So go to the documentation, scikit-learn documentation for random forest classifier, and then you will find some hyperparameters. In my case now, I'm going to just copy and paste them from my prepared code, because what we have here is we have the number of estimators, we have the max depth, we have the min sample split. Basically, this is the number of trees in a forest. A random forest is just a collection of decision trees. So we have different number of decision trees. We have a limiting depth, so saying that the tree cannot have more than a certain depth. So none is unlimited, 10, 20, 30. Then we have min sample split, how many samples we need to split a node, min samples leave, and then we also have max features, which limits the amount of features. So these are just some hyperparameters. We can now say that we want to have a random forest model, so a random forest classifier. We're going to set n jobs equal to -1 to parallelize all of this. And we're going to add the random state of 9 again. And then we're going to say grid search is equal to grid search CV. We're going to pass the model, we're going to pass the parameter grid, and we're going to say we want to do a threefold cross-validation. What this basically means is we take the data, we split it into three folds, we use 2 for training, 1 for testing, and we do that for all the combinations. So maybe to show this visually, this would be all of, okay, this would be all of my data. I make a split like this. I use these two for training and I evaluate them on this one. I evaluate the model on this one. Then I use these two for training and I evaluate the model on this one. And then I do training on these two and I evaluate the model on this one. That's what threefold cross-validation is. So for every combination of parameters, we're going to do it 3 times. So if you have a large data set, you want to reduce this, you want to keep this smaller. This training works quite quickly, so we're going to just, easily do a bunch of iterations. So finally, what I want to do also is I want to say njobs -1 here because I want to parallelize this process as well. And when I run this, or actually not when I run this, but when I say grid search dot fit, and now I'm going to use xtrain and ytrain, I'm going to do all of this for multiple models. We can actually go ahead and say verbose equals 2 to get some more information. You can see we're fitting 3 folds for each of 324 candidates, totaling 972 fits. Why is this? Why are these the numbers? Because we have one forest is going to have 100 estimators, no limit, 2 here, 1 here, and square root. The next one is going to have 100, none, 2, 1, log 2. 100, none, 2, 1, none. Then 200, or actually 100, none, 2, 2 square root. So all of these have to be multiplied. And while this is training, we can actually do that. So we can actually open up, do we have a calculator? GNOME calculator. How much do we have here? We have 3 times 4 times 3 times 3 times 3. That is 324, and we're doing threefold cross-validation, so 972. So this seems to be done right now, and as a result, we get the optimal classifier. So we can say best forest is equal to grid search and then best estimator. So we can take a look at the best forest, and it has 500 estimators and nothing else. That is the best result. So all of the others are kept at default. This is what it means when they're not listed here. Random state 9 is of course fixed, and jobs -1 is also fixed, but that is the only thing that we change. Now it would make more sense now to comment out all of this and see if we can get an even better model by providing, for example, 600, 700, and so on. So I can just run this, and this would result now in still 500, so it seems to be a very good number. We're going to keep that, and we're going to now do a feature importance analysis. So we're going to open up a new section here. We're going to call it feature importances, and we're going to say that the feature importances, actually for this we're going to use NumPy SMP. We're going to say that the feature importances are equal to best forest feature importances underscore. The features, so the feature names, are best forest feature names in underscore. And the underscore is just a convention in scikit-learn that these are things that are the result of training. They're not there by default. They have to be calculated, so to say. We're going to say sorted index is equal to np arg sort. We're going to sort the feature importances so that we know which indices are, which are the indices, so that the whole thing is sorted. And then we're going to say sorted features is going to be equal to features sorted indices, or sorted index. And then we're going to say sorted importances is going to be equal to feature importances sorted index. Oftentimes what I also do in these tutorials is I zip, and then I basically do sorted zip, and then I provide key is equal to x1, lambda expression x1. This is also one way to do it, but we can do it like this as well, which is maybe easier to understand for some people. And then we can choose colors for the bars because we're going to visualize this using Matplotlib. We're going to say the colors are PLT color map yellow and green, or yellow to green, sorted importances divided by the maximum of the sorted importances. So basically we want to have the most extreme color for the largest value, and that's basically just scaling it. And now we're going to say PLT bar horizontal, so bar H, sorted features on the x-axis, sorted importances on the y-axis, or actually, no, sorted features is going to be on the y-axis because we have a horizontal bar. Sorted importances is going to be on the x-axis, and the color is going to be colors. Then we're going to say PLT X label, feature importance. The Y label is going to be features. And we're going to say PLT show, and maybe also a title, feature importances. So when I show this, we can see that we have certain features being way more important than other features. Now, before we analyze this, I want to also take a look at correlations before we do any random forest classification. So in the data itself, we might find some correlations, and I think that this is going to be a good learning that this doesn't have to be exactly the same as the feature importances. So I can import seaborn as SNS, and I can say that in a data frame, I can have correlation. So if I say df correlation, I will get this table here. And I can just say SNS heat map of this correlation matrix. I want to have the annotation equal to true. So I want to see the values inside of the heat map. I want to also have the same color map as before, which is yellow, green. And I want to say PLT figure size is going to be equal to 1210. And then we can see that these are the correlations before we do any training. So this is just how the data correlates. And the target correlates very strongly. You need to also consider negative correlations, because negative correlation doesn't mean it doesn't correlate. It just means it correlates the other way around. So it's an indirect proportionality. To maybe make this clearer, let's go and apply the abs function onto the correlation. We're not really interested in how they correlate, but only the magnitude. And then you can see that the strongest correlation between the target variable and the other features is between xang and old peak. So if we go to the data, what is this? This is the column 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I think 9 and 10. Exercise-induced angina, and then we have ST depression induced by exercise relative to rest. I'm not really sure what these mean, but these two features seem to be, if you just look at the correlation, the most important ones. And then we have the chest pain type, and we have the, what is that? Maximum heart rate achieved. So these are also important. But when we look at the feature importances, we can see that the chest pain type and the, what was it again? The maximum heart rate achieved are more important than old peak, and definitely more important than the exercise-induced angina. So this doesn't seem to be important at all for the random forest classifier, but it has a very strong correlation. So you can see that this is not always necessarily equal. A strong correlation doesn't mean that it's necessarily important for the decision making when it comes to classifying whether someone has a heart disease or not. So that would be my conclusion. Actually, maybe one more thing, because we didn't evaluate this. Let's see if our best forest actually outperforms the other forest. So let's do a score X test and Y test. And we get 9853. What did we get before? We got 536. Yeah, it's the same. It has the exact same score. Let's see if it also has the same recall. Y predictions is going to be best forest. Or actually, let's go for the ROC. So let's just, what happened now? Let's just go and do this, but with the best forest. I'm just interested in that. Yeah, looks the same. And now maybe also let's do the recall. So let's go and copy that. And let's do it here as well. I think this is going to be equal right now, and maybe this is just because the data is too simple and we don't have a lot of data. Best forest. Yeah, it seems 9859. What did we have here? 9859. Okay, so it has the exact same performance, which doesn't have to always be the case. Sometimes it can be worse, sometimes it can be better. But yeah, the most important feature when it comes to predicting whether someone has a heart disease or not is the type of chest pain. So not if someone has chest pain, but the type of chest pain. We have 4 values for that. And then also the maximum heart rate achieved. And then CA, what is CA? CA is the slope of the peak exercise ST segment, whatever that is. So I'm not a medical professional, I don't know what that is, but yeah, this is an interesting analysis. Our model performs quite well. Of course, what you would do now if you want to use this, which I would not recommend, this is just a coding tutorial, but if you want to use this, you could just take the model, best forest, and do predictions on new data. So you just take new data and you make predictions on the new data. You just have to format it in the same way, just pass the numbers in the correct order, and then you're going to get either the prediction, or you can say, give me the probability that someone has a heart disease, and then this works as well. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.